All right, so we are live. Hi, everyone. I'm really excited today to discuss amazing course we came across a couple of months back. It was about computer vision in AEC, and Rutvik reached out to me on Twitter that, okay, look out this course. It's taught by Professor Hiro, and it has some amazing applications. So we started reading slides, and we thought it is such a course that a lot of people can benefit. So we started discussing what are some interesting applications in AEC, and that's how we thought, okay, let's do a collaboration and talk about the course so that we all can brainstorm and learn from each other. So thanks a lot, Rutvik, for doing this.
Thank you, Mayur.
Yeah. And he's currently associate data engineer at Blueform. It's an amazing company, and like definitely check out Blueform. They recently also did a workshop at Cadria, and it has some amazing applications for generative design in AC. And I got to know Rutvik from one of his Medium blogs. So if you like reading articles, definitely check out his Medium blog.
Thank you for the intro.
Yeah. All right. So what's the goal for today's session is we'll be reviewing the first floor lecture slides from this course. And um, so our goal is to focus on what are the key algorithms discussed in those slides, applications in our day-to-day workflow, and how to implement those, and what are the pros and cons of various approaches. So I hope without much ado, we can just jump into the course. Cool. So, all right. I think one important distinction which it makes is like the way we see the images versus machine. So it's all just a matrix and pixel values from 0 to 255 and just three layered data, and it's all numbers. And the rise of computer vision, I think, has been increasing. So initially there was like ongoing research with just like image processing and other algorithms, but then with the rise of internet, we got a lot of data, and then machine using deep learning approaches, a lot of applications have been developed because we have so much data we can use and drive new insights from. So you might have seen like applications like space geometry, where based on the images, like 3D reconstruction of that model is done, and also semantics, where object detection, segmentation, and those kind of operations you can do. Rutvik, feel free to jump in if I'm missing out any key points.
Yeah, absolutely. Right, because it's an interesting course where they have, I think, customized it for the people in AC with the problems we face or the data which is useful for us. And they went from image processing algorithms, then they dive into machine learning in the fourth lecture.
Correct.
So I have few points. I'll talk about them when it comes.
Awesome. Yeah, in this slide, as you can see, it's also apart from shape recovery, you can do depth estimation, and these are some images of the sensors which you can do use to do that. Scenery construction, tracking. I think this has also a lot of applications in construction, where you might have seen like Boston Dynamics robots doing autonomous tracking and site inspection. So huge application in construction monitoring using computer vision. Also like 3D scene parsing, where you can parse various objects in that particular image. As you can see, this is segmentation.
This is the human level understanding, right?
Mhm.
They're talking about the broader aspect where we can classify, or we are using masking techniques to identify different components of interior.
Correct. Like without any filtering, we just assume, okay, this is floor, these are grouped into furnitures, clustering by intuition. I see. Cool. Yeah, so this is a straightforward way where we can see how they're using this.
But is that like a classifier that's automatically masking parts of the interior space?
So in I believe in this slides they are portraying that even humans, when we understand a scene, we automatically classify that, okay, these are all the furniture in the scene, this is the floor, this is the ceiling. So even human understand the scenes through this kind of segmentation. So this is not using any algorithm, this is the way humans understand the scene.
Oh, I see. Okay.
Yeah. And now they're comparing it with machines where, yeah, basically each pixel carries RGB value, which is shown in the image. And ideally, what we want to achieve is what humans understand the scene, machine should be able to do the same using the algorithms or processing. But it's challenging. It's RGB data. How do you segment it? How do you differentiate it between various objects in the scene? Because if you show machine an object and let's say you classify and train them in one particular orientation, but if you change the lighting, the same object will have different RGB value in different lighting scenario or different orientations. So it's not that straightforward.
I think
Here,
they compared the human brain versus the machine classified data in the initial slide.
correct. Yeah. And now they are talking about what are some reasons this course would be useful. Like definitely building errors and scheduling can be improved using those algorithm.
Yeah, and it's actually very explainable slide. Like AI cannot completely eradicate these errors or the overcosting, but of course it can reduce it. And I read about the Berlin airport. It had a lot of errors due to which it had delayed, like fire system safety errors or design flaws.
I see. So are we then like trying to communicate that there are like human errors in during construction or during like measurement and let's say assembly of furniture? There are a few tolerances which we do, but with the help of vision we can reduce those errors.
Yeah, I think they've been talking about various parts which can be automated, or like for some tasks you require a lot of expertise, time as well as cost. And what if we can automate that? What if we can reduce the human errors? I can see the cost which was increased in both the examples they have mentioned.
I see. Yeah, one for sure application I foresee is like, let's say you are arranging the mechanical duct in ceiling. One way you can do it, you measure through like from the edges of the ceiling and the wall that what's the exact location you should place that duct. Another way could be using vision. You do 3D reconstruction and import the digital model and exactly identify where should it be placed in the live camera feed. So maybe that can reduce human generated errors for assembly and increase the accuracy.
That's interesting. I'm more curious. Like, there's almost like $1 billion difference that sort of like is shown there. If you can just one sec, just move back to that slide. So the current and the expected, that's basically like the deviate because of the errors and the deviation. Like the expected was 1.8, but then the current cost is 5 billion. Is that what this data is saying?
Yeah, I think due to the
Uh,
delay and errors, the cost increased
uh,
by this much
Gotcha.
amount.
Yeah.
It's almost like
That's
300
yeah.
3 times.
Huge,
Yeah,
it's huge. Yeah.
cool. So we know that okay, there are definitely potential for reducing building errors, improve the schedule and cost using CV. And I think this is just like a class interactive exercise.
They were saying like it's not AI versus industrial expert, but it's acting like a system. So AI plus industrial expert. I think that's what they meant.
Mhm. Yeah, and I think yeah we discussed like the intent of the course is to identify limitations, bottlenecks of this, and how human and machine can be worked together to solve and improve the accuracy and reduce the building errors. Yeah, we all know this, like using data evaluation and metrics. Yeah. What was the main? So I think they're
Importance of
identifying.
data here is like the challenges. These are the challenges in computer vision. So they could have added it in the machine learning segment.
I see. Yeah, I think these are crucial points. That okay, if you change different scale, it's challenging. Different illumination will change the RGB values for the same object. Scale variation can also be challenging for machine to identify it. Deformation, background color, clutter. I think for segmentation, this might be quite challenging. Occlusion and interclass variation. So I think they will go deeper into like the later lectures, how like data challenges and CV applications in machine learning. But this is like just an overview that here they are like using machine learning classification of various objects in a scene.
But it's challenging in real life. Some places we can do that.
Yeah. So okay. So even if we have a lot of data, it's not that easy to develop a computer vision machine learning model because of so many challenges of changes in scene scale. So I think as maybe as a part of our job when we are developing this model is how do we have that diverse data so that it considers this variation in the scene.
Yeah, extremities and outliers should be kept in mind.
Correct. All right. Anything else you think we should discuss? I think we got the. Oh, there
I
are.
think the rest is
Yeah.
logistics and assignments.
Yeah. So this is like point cloud data, space parsing, detection. It's pretty straightforward.
So this disjoint space parsing, it's like manually labeled, is it? Like the yeah. In the stage, it's like each space is manually uh attested a false color value. Like, is it sort of like are these the like the labels?
That's a good question. Like,
I think they have provided the labels. They have the work on one of the websites to write the building parser. That's what the project is named.
but is it done manually or through any algorithm? I think it's manually because I'm not sure how the algorithm knows what kind of
Yeah.
rooms it is. So it's
I think this is like they're generating the data to sort of train the model or something at this point. Maybe like it's manually.
Mhm.
Or it can be even semi-automated, like they are doing 10 to 15%, and then
Mm-hmm.
Yeah, one way I can think it can be done automatically is like if let's say we have the building model in Revit, we
yeah.
know the dimension of the room like in geo location, and then when we get the point cloud, I can do some automation that okay, if all the points lie in this bounding box, assign
Yeah.
this room.
Mm-hmm.
I see. Okay, so from input points to voxels to boxes. I think yeah, it's important that when we do like this kind of scanning or point retrieval, we don't get the exact clean plane, which we ideally have in the digital model. Like there are some voids, so there are some post processing you do to get those clean edges and planes.
So they are using three-way output like voxels, boxes, and points too.
So the way like I haven't looked into it, but I'm guessing that let's say from here you get discrete point, and then you localize all the point using grid and voxel, and
Right.
once you have those voxel you can combine all the voxels which lie in the same plane to create planes.
Oh, so it's like it's 3D data that's like from the point cloud model. It's sort of I see because one more I feel like an application that you can use was like you have like shape detection built into like OpenCV. So like just from like these elevation like images, you can actually like detect, for example, rectangles. So again, like based on different like RGB values, and I can easily sort of like see this whole process sort of like writing a script to automate detection of like the background backplate and the bookshelf and sort of like segment it uh, based on different colors, like just like what's happening here.
Yeah, I think they have spoken about shape detection in lectures that they have mentioned about hook
Mhm.
transforms.
Yeah, like in the next few lectures they, like as Rutvik said, hook transfer from like creating specific lines and shapes. But let me check what they have in.
Yeah, this site I was talking about, building parser.
Okay, method will give some insight. Okay. So how are they disjointing? Like from this is like connected data of all the rooms, and then they are
Yeah.
disjoint.
There's a the paper is yeah.
Hierarchy. Okay.
Oh.
Oh, I see. So I think using this difference in density, they are identifying the space partition and then pooling and non-max suppression to clearly distinct that okay, separate this rooms from this corridor from this rooms.
Mm-hmm. Yeah.
I think they would again go in detail for that room. They'll go in specific corners and separate
Okay.
furnitures and all.
Okay, so I think then in order for this joint space to work, I need like a floor plan or like a top view image because that's how I know the difference in the intensity in using histogram, and then I can just clearly divide that space.
That's another question I have. So they sort of like shown that they're using like point cloud data. So in that sense, like are they using like an implementation of like PyTorch 3D here, like, or is the point cloud data being translated into images and then is it just a CNN that's
Um, I think there are various ways to generate point cloud data. I can even use like a laser scanner and generate point cloud data without any CNN or machine learning framework.
oh no, to refine my question, what kind of data input is sort of like going into that particular flow chart? Like it shows that it's 3D data, like point cloud data. So in that sense, are they using like some sort of framework of like PyTorch 3D to like
Oh, okay. Once you get the point cloud, how are they segmenting it, or like
yeah.
UI? So I think to get the histogram NMS, you can also do it in using OpenCV.
Mm-hmm.
But
I think there is
yeah,
a way to generate mesh from the point clouds as well in Python. So they generate the mesh and maybe then
yeah, I think I got it. So this says applying using ransack and hug. So this is you can do it in OpenCV. These two algorithms.
Mm-hmm.
All right. So I think I might have got it. So there are challenges once you get this like in your image like you will have like this kind of point cloud. So I think in order to get straight edge like this, you need hug transform, and I think we'll go deeper to to make those linear boundaries. So
Interesting.
yeah, so this is basically a image processing algorithm without any machine learning.
Mm-hmm.
Let me scan quickly if there's anything else. Segmentation, neighborhood. Oh, this is important.
Oh,
oh the graph based approach, right?
yeah.
Yeah, and I think that's important because like one can use this connection for other analysis as well, how the rooms are connected, accessibility, and
It's like that syntactic.
but then I'm thinking like, is this graph relationship done manually or they identify the openings in the wall and made those connections? Vison generate point cloud, create the neighbor graph. Okay, how are they creating the neighbor graph? Okay, this.
Oh yeah, the segmentation. I think they're using the graph-based approach. I think they had one slide about it. We couldn't find it that day also.
Okay, so we compare our method with Ren's again. So they're definitely not using that. So
But only Hogan ransack, which means that only edge using contour detection, some sort of
hmm.
creating depth maps and then getting.
Yeah, I'm just thinking. Okay, they're comparing their results with this two, but what's their model? They're doing object detection. That's
Yeah,
hmm.
so I guess the segmentation is sort of the false color labeling is happening autonomously then. Like that's their US.
Mm, mm, mm. So if they're just comparing that using deep learning based segmentation, it's performing well over Argon Ransack, or they are adding their own algorithms. We propose a detection based semantic mask. Okay, parsing raw point cloud.
Yeah.
Hmm. So if it's parsing in
So you give it a point cloud model and it automatically segments all the spaces. And I think the individual elements as well of a particular room. So on a broader scale, it sort of like segments each room in the program, and then it can also go into like each room and segment like the elements of the room.
hmm. Okay, so I think it says also that parsing by detection. So for it does some detection analysis and identifies those rooms and then make it disjoint. And it's using 3D sliding approach, yeah, like operating on a voxel grid. Hmm. That is shown here. That voxel information.
I'm just very curious to understand like the training data that was used, the models that they sort of like.
Yeah. So they have like indoor data set which
Mhm.
they are mentioning
Oh,
here.
yeah.
Okay, I think it's 9:35 and we just have finished one slide, so maybe we can come back later at the end.
Yeah.
But it's a good paper to discuss, like their approach, how they are parsing it.
It's
It will
really
be
interesting.
useful. Yeah.
Yeah.
Right. So in the intro lecture, what else we have? Natural score. Hmm. Are they telling how they are getting the natural score here?
No, I think they just are talking about the applications further after detecting or
Yeah,
segmenting different.
I see. So, hmm.
No, it looks more like you sort of like input the point cloud and it's able to sort of generate or predict how much light, like different daylighting metrics like illumination and natural light is sort of entering. Sort of looks like that.
Yeah,
Yeah, it will be for the application right after you detect the
Oh,
furniture.
right.
Then
Oh, yeah, that makes sense. Yeah, like some sort of a simulation and uh,
hmm yeah. I'm thinking like since they have the input, they have the window openings, and they pass like exterior light, they might be able to generate further simulation. And also, yeah, using that data, one can do spatial analysis and identify what's the number of chairs in that space, total square feet area. I think, yeah, this is quite. I think this would be useful for remodeling or like even for architects where they want to try out different options of an existing space. Like, should one remove this wall and add another element, or what are some furniture which can be uh, suitable for this area? So, and in like I don't know, but it looks like the current procedure is one would remodel this space in a 3D model environment, try out various options, produce rendering, and then showcase it to client.
I
But
mean, you can
using
also use conditional GANs right now, right? Like you can use a pix to pix model to uh like the whole facade prototyping stuff. Like you can sort of explore different options by just giving different inputs. But yeah, I mean, it's interesting.
yeah, we had discussed that startup, like there was, what was that name of, uh, furniture removal and space manipulation. They were doing using the AR based approach.
yeah,
Fetch or
it,
Hyper.
No, I think it
no,
was something visual, something. Visual stager.
Oh, interesting.
yeah, even like in augmented reality apps, I think I was just discussing with Rutvik on the other day. For them to place an object in reality, they need to identify the planes for floor, wall, ceiling, scale the object with the distance. So they need to know the depth map data. So that's why like CV, if architects or engineers wants to play with those mixed reality VR AR applications, it's also helpful for them to know what's going on in the background. Cool. So that's it for slide one. And Rodwig, should we move on to slide lecture two?
Yeah, I think if we go on, since we have not taken this course, we can just talk about it for a long time.
Cool. All right. So I think the second lecture focuses more on the low level features, edge detection, how the hub transfer ransack works, canny edge detector. And I think this was quite important. So there, because edge detection is not that easy. Like, and if you want to know how they do it, this lecture goes into the various challenges of extracting and making edges through points. Cool. So
So it's still the image processing approach, OpenCV approach, you can say.
correct, you're right. And yeah, they are identify, want to know object, its location, what are some contours and occlusion attributes of that object, which is like our way of compact mental representation of various objects in the scene. So we want like this four major attributes. What are different objects in the scene? What's their location? Their relationship with other objects? Color, material of those objects. Yeah, and these are low level, high level features. Cool. So now I think what's the most intuitive way you can identify edges? So if you have like this sets of pixels, you can see on an edge the intensity of pixels on the left would be lower than intensity on the right. So the difference in that intensity, one can use it to identify an edge. So
Human boundary, as in the predominant edges were identified by humans, and then they introduce a couple of algorithms. Canny edge for the intensity difference,
mhm,
contour based detection.
correct. So now they are showing like what are different areas where edges occur. So one, if there's surface discontinuity, as you can see here, there are like three edges occurring there. If there is depth discontinuity, as you can see here, it we want edges on that part. Even surface color discontinuity and illumination. And yeah, they're talking about even segmenting, which will they will discuss later. Yeah, I think I want to refer to this Stanford course for to get some idea before we move on. Mm, yeah, so I think image gradient is very important concept before we move on to understand it clearly. So as you can see, like this basic formula of derivatives delta x, and we have this pixels, and this is, let's say this x plus 1, it's a discrete data of all the pixel values arranged in a grid. And if I just take delta x equal to 1, which is in our case that how I am moving one pixel ahead at a time, it gives those formulation for image processing. So if I want like a backward derivative, forward derivative, these are examples. And uh, if you have a, imagine just the image instead of 2D images, it's just, let's say this is our image. Let's just analyze only one row of that image, which are a lot of pixels in that row. And if I want, let's say, the differentiation of this pixel, I want this pixel minus this pixel. So if I have this small filter 0, 1, minus 1, it will multiply fx minus fx plus 1. Like the point is, if you run this kernel throughout the image, it will give you the whole image gradient. Yeah, so you can do like forward minus backward or like various ways to do filtration. So this is fx, as you can see, and this is f dash, where like 15 minus 10. Okay, once we are analyzing this, is it a backward or a forward filter?
It's a backward one, I guess, right?
Yeah, I think it's this is 15 minus 10, and then this is 10 minus 15, which is this 2.
Yeah.
10 minus 10. Yeah, so you see, and that's a basic one-dimensional gradient. And if I'm going in 2D, I would like to do in row and column of that image, so fx, fy, and this gives gradient magnitude and gradient direction of like, and I think this we'll see soon that how we are doing gradient in x direction, gradient in y direction, and like this tan function can also give like x and y. I can easily get horizontal and vertical edges, but if it's, let's say, curvy shape, like this tan theta gives me the direction of that edge based on that gradient. All right, so intuitively, if you look at this, it's just uh, this 3 strip and 0 minus 1,
I
1
think
and
there was a
3.
graph too, right? That they are shifting the gradient, and there was a graph with noise, and then they apply kernels. Was it in
Correct.
this slide, or I don't remember?
Yeah, I think it's on the original lecture. We'll jump on that soon. So if you look at this filter and you look at this image, you inherently feel that okay, this is there's a pixel difference and there is an edge over here, and if I want to extract this edges, what kind of filter, like let's say 3 by 3 filter, I should pass on this image so I can clearly distinguish the vertical edge from just those pixel values. So if you apply this horizontal filter, like uh, as you might have think, there's no horizontal edge in this image, so everything should be 0. But since if you apply a vertical filter, you will get this vertical edge, and that's how, in order to do edge detection, we need to know what kind of that kernel, like in this case 3 by 3, which we should pass on so that the output image results in those edges which we can extract and work upon later. So this gives like this kernel in x, this in y, and this is a basic simple edge detector. And I think we it's important that we relate back to the derivative concept. So the point here is, like, this is our image and we know the intensity changes here, and when we uh, for fx, and since there is high change over here, no change over here, in the derivative it should reflect zero change over here, high change over here, and those high changes which are here are our edges. So this derivative function on fx, those spikiness gives inside our edges.
Peaks of first derivative act as error in simple images, and the ones
Correct.
without any noise.
Hmm. Yeah, and this is basically showing gradient on y, x. Right. I think this to conclude, we are interested in this gradient magnitude, and we saw it under root that dfx square plus dy square, and those combined values will give this basic edge. So I think we now know that okay, if there is a change in intensity of an image like this, those those high change values will give us peaks in gradient, and those peaks gives us edges. So uh, life is simple if we just do a gradient and we are able to do it. But not all images are super clear. There are noises in those images. So imagine like this is a simple image with noise, and ideally the image should have like a horizontal line like this, but since we have noise, we have so much changes. And for every change, as we saw earlier, it will produce a peak in gradient. So this is our gradient. And if we input this image, the gradient is telling there are so many edges instead of just one smooth peak. So that's why we want to reduce noise first before we identify those edges, because that can give us very erroneous edge results. And this shows an example. Smooth the image, forcing pixels to be different. And this is basic. Like you can do mean. What that is one way to reduce noise. You can do Gaussian smoothing, where instead of 111, it's 1 to 1. So you can identify various weights, and depending on your smoothing intent.
So Gaussian is a filter for smoothing the noise to make it binary.
Correct. Yeah. I can smoothen through Gaussian. I can smoothen through mean. Like it's just like whatever kernel values you decide, you'll get a
Mhm.
different smoothing output, mean, medium, and you can compare. And I think this is one of the most important image.
Yeah.
So we saw there's a noise. We saw we need to smoothen it, and one way to do it is using Gaussian kernel, as we saw, like 1 to 1. What we can do is pass this kernel throughout the image, like if there is an image, I'm passing and doing like a operation. So f star g gives me original image and a kernel which scans the whole image, and now we see all the noise which was here is removed, and we get like a smooth line like this.
We get a convolved image when
Mhm.
you pass the kernel throughout the image one by one. I
Correct.
think even the in concepts of CNN, you can even define the spacing between two kernels, like by what it should shift by 1 or 2 grids.
Correct. Yeah, like there are many details, like small variation that okay, once you're passing the kernel, what are we doing about the corner? Are we averaging it, or are we keeping the same value? Like yeah,
Yeah, so
there
they
are
provide 000 on the edges.
correct. So yeah, there are various padding and things. So
Padding, yeah.
ultimately, yeah, all we want to identify that edge here is this peak ingredient which we saw earlier. So we did that this time with image with noise, just by adding a smoothing function and doing a gradient. So that's the point, uh, which is important, that just gradient won't work with noise. We need smoothing function. And there's one property here which is quite relevant. So initially we saw, in order to get this peak edge, we had to perform three operations. Basically, we had to first compute f dot g, like convolution over the whole image, and then we did differentiation, and it takes a bit of compute time. So using this property, I don't need to do differentiation over the whole f dot g. I can just do differentiation over my kernel filter and then just do simple multiplication. And this also gives me the same output as we saw earlier. So
So we are doing derivative of Gaussian filter.
correct. So instead of doing multiplying Gaussian filter with image and then do differentiation, we can just do initial differentiation of Gaussian filter and then just multiply it. So yeah,
Yeah, so that takes us to the Laplacian graph, which is that way.
correct. Yeah, so this is our Gaussian filter kernel, which looks like this. If you do this is like as we saw earlier, central differentiation. It gives derivative in x like this. So this is what is differentiation of g dg by dx, which we
Yeah.
saw. And similarly in y you can do, and this is how the gradient looks like. Cool. I think those are few points I wanted to share. So we got the intensity, changes in intensity, which is reflected in derivative, which gives us edges. Gradient magnitude, we saw gradient in x square plus gradient in y square square root, that gives the magnitude.
Yeah.
Then they'll talk about the noise, which we saw if you do work. Yeah, I think this we already covered. Cool. So this is how one can find an edges in even in a noised input. Then let's talk about trade-off. So as we saw, like uh, in a smoothing function, I can use a mean function, which is just 1, 1, 1. I can use a Gaussian function, which is 1, 2, 1 for smoothing. And here, like depending on the size of the kernel, the values of the kernel, the output is affected. That how much smoothing you want, because more smoothing will also affect the reduced edges, like less sharpened edges, or some of like there is very small minor fine detail edge versus a long edge, and while smoothing you might miss out this edge. So a lot of smoothing will also create a loss of finer details in the image.
So smoothing depends on like number of size of kernel depends on the priorities of your output, whether you want stronger edges or you want the noise removed.
Correct. And here they are identifying what are the challenges. Oh, I think this slide has like, so we want is true edge, and then because of noise we get poor edge, and there's also localization issues where the edge should be detected as close to the true edge, and there are also like too many responses, uh, which we should not want, so we should minimize the local maxima. So ideal things we want from an edge. Cool. Okay. Now we saw simple edge. Then what is canny edge? And I think there is this image which is really good. So the main component of canny edge is uh, let's non-max suppression. So let's say you identify this edge using that tan theta d differentiation in y upon differentiation in x. And what you do is you scan on a threshold around it, and you say if in that region around that dominant edge, if the values are lesser than that particular threshold, ignore it and just take this maximum and go ahead. So a lot of non predominant edges can be removed through this non-max suppression.
That's what they did in that hotel photo, right? You were discussing how the predominant edges were visible and how the others were removed.
Which slide? Oh, this one. I see.
Yeah.
Correct. All right. So I think there was also another component of threshold. Yeah, threshold and linking below, not an edge, above, strong edge.
So basically thinning the pixels or the wide uh, ridges they called.
Mhm. Yeah, I think I don't want to go much in detail, but there is a really good image I saw. Yeah, I think this, where you can see using that gradient, you can, in that perpendicular direction, you can remove those thin edges
Okay.
before, after. And the last is hysteresis thresholding. Yeah, I think when they are referring here, uh, yeah, high threshold to start edge curves and low to continue, and for high, like there's in between weak edge. So they're referring like if there is a strong pixel around this, how. Cool. So I think now we know how to identify image, how to uh, work around with noise in an image, how to remove weak edges in an image. But still, like if there's let's see image like this, it might give us an edge like this. How to get like clear cut straight lines, and which for plane detection and for various other reasons we might require. So that's where uh, hook transfer comes into place. And this is a bit complicated concept, I must say. So imagine, I'll do my best here. So let's take an image. Yeah, so any line in this can be expressed like y equal to mx plus b. And if you see like an xy curve, this, let's say this is the line mx plus b, but this also can be represented in another space where a perpendicular line with distance p and a theta. So all we want to do is uh, identify for each point like what are the possible lines to it, and using the predominant line, let's say from here, I get votes on the out of these possibilities. uh, each each line can be pointed out as a like line is being transformed into a point in this new space, and it has like same the perpendicular distance and theta. So if there are, let's say, a lot of lines with same p and theta, it identifies that okay, there should be a line with this p and theta slope in this direction.
Yeah. The other day I was reading about the Who transforms, and I found out that it is also used where we want to detect broken shapes. So it's also useful for that part. It can detect the broken parts as well.
Correct. So yeah, I think the bigger idea is if we want like lines, circle, like shapes, and out extracted out of that image from just edges, we need a new space where we are transforming all these edges, identifying what are the possible lines to those edges, and then based on the voting, uh, the predominant line is selected and then being drawn upon that image. As you can see, like there are a few lines here.
Yeah,
Cool. And again, like there are challenges in line fitting, as you can see in this image. Like there's clutter, extra edge points, you know, only some parts of each line detected. So that's where like voting technique is comes into the play. And because we have this outlier, random cluster, extra edge points, uh, random sample consensus uh, proves to be a better algorithm to remove those outlier and identify what's the ideal fit. So it basically what it does is, yeah, think it randomly selects group of points and find ideal image. I
like it
think
does
the
various iterations and then chooses the best fit lines, like which has in a certain given confidence interval the highest number of inliers or the points lying in that region.
correct. So just for an example, if there are like 2 points like this, it'll make a line. What are some inliers? If it's identified 2 points like this, it makes a line. What are some inliers? And it's so random part is about random selection, and consensus is about most of the points falling in that width. Yeah, within that threshold. And if most of the points agree that okay, if most of the points agree that in the threshold that this is the ideal line, it will go ahead with that.
Yeah,
Cool. So yeah, as you can see, based on your start point, there are like 7 inline points, 11 inlier points. So the model says okay, this must be the ideal fit. Cool. So what else do we have in this lecture? So we saw lines. There are also like circle, other shapes can be identified using Rensec. And actually I was implementing a similar algorithm using point, but like this is for circle where I was,
mhm.
but I think the I should have manipulated the radius, but I think using basic CV you can do either circle or basic like lines and find it in those. Cool. So how we can use this? So if it can be used to identify the flatness of concrete slab, where if there are some points in that 3D point cloud which are not in the same plane or it's undulating, you can identify using it.
Yeah,
Similar
crack
flat.
detection. I think it's a very widely used application of line detection, edge detection.
Mm-hmm. Yeah. So we saw edge detection algorithms. You deploy it, and I think they shared even a collab notebook, so you
Yeah,
can do some basic CV. I think based on their notebook, they had some example that take a husky image Then depending on different threshold values of Kenny, you can find more edges.
Yeah.
Correct? Yeah.
Yeah.
Cool. And also at last they are identifying that okay, Lionid just applying OpenCV on those image and finding cracks. It's not that easy. There is also a lot of challenges based on it, which we discussed, like some of it earlier, that illumination, different environment can also
That's
lead to.
where machine learning can come to the picture, where data plays a crucial role. So you
Correct.
can train it on different extreme data sets, like has like very less illumination or highly blurred images.
Yeah, so like there are some cases which one can't identify earlier, or they
Right.
can't make like a algorithmic identification that okay, based on this outlier, remove it or something. So that's why machine learning, a data driven approach, is more crucial. Cool. Then from 2D we are now moving into 3D point cloud, and that's the next lecture they are focusing on.
Yeah.
Anything else, Rutvik, you wanna say before we move on to the third lecture?
No, I think we have covered details too.
Awesome. All right, so let's move from pixel to 3D. I should zoom it out. And just like what is semantically rich 3D building, it has all the object information, spatial information, building information, uh, and those relationships.
Right.
Yeah, and like few of the problems they are sharing is like there's incorrect documentation of existing as built, sometimes out of date documentation. If we want to do 3D reconstruction using like I think image, it's very labor intensive, time consuming, and also construction issues, incorrect topography.
So they are talking about on-site construction issues faced by them personally, and it can be again many others.
Yeah, like to make a digital twin of that building, like they're saying you can't just use like Revit or Rhino model because it doesn't reflect the on as built condition. You can't even do all the modeling from scratch. It's labor intensive, and it
Yeah.
also virtually you can't like see what are the on-site topography. So basically, you need a vision-based as built documentation to make it more accurate. Cool. And then they're identifying what why is it important, and I think we all understand that renovation is gonna be a big industry in future. Cool. So yeah, I think the traditional way they are saying is you go on site, you take a tape or something, you measure it, you update the model uh, in your modeling environment, and then document it. The state of the art practice is using sensors like lidar or various other examples. You do measuring using the sensors rather than doing it manually on site, and it will generate the model.
Yeah.
Yeah, so don't do manual modeling, just use it using the sensor data from the point cloud. That's what we got it. Cool. So reconstruction, so basically image or uh, whatever data you capture through your sensor, make a point cloud, make a semantic understanding through tagging. Okay, I think they are export model 3 weeks. And the manual tagging can be automated. So this is the crux of the whole lecture where how we are using.
Automating the manual tasks,
Mhm.
issues which could be solved using that automation. Comparing, they are comparing, I think.
Correct. Cool. So what are the different ways we can do it? One is just using our phone camera, RGB data. Another is using depth data from Kinect, Google Tango, which is called 2.5D. There is this 3D data sensor using Leica Faro, even LiDAR, like I assume, and it generates point cloud directly. And I think this direction will be pushed using point cloud because in recent iPhones they are embedding LiDAR sensors, so anyone can just scan it and generate
Yeah,
mesh and point cloud. So a lot of more data will be generated in upcoming days in
yeah.
this.
I've just seen a project where they were doing something, uh, road safety detection, like crack detection or condition analysis using the iPhone LiDAR data.
Correct. Cool. And this is like basic. They are identifying how it works, where using that sensor, the project on a plane, and depending on the lighting which reflects, they calculate the distance and the depth map.
Yeah,
And same using laser scanner, you can get the depth map and the point cloud finding correspond. I have seen like few deep learning approaches where like they are taking images from different orientation, and even you can reconstruct using just from RGB data.
okay, that's interesting.
Yeah, cool. So I think a pr- I have seen. Have you seen Nerf? It's very popular these days in computer vision world, where they're using a different approach than uh, conventional deep learning. Like from few scan, it's generating that. So you take like different angles, do rendering along this ray.
So they're creating a video sort of thing,
Yeah,
continuously
video.
moving.
Yeah, video, and I think also the virtual model based on different images, they find the intersection of that orientation of that image in this and re-render it. So
I think I have seen it. Yeah, yeah, some interior. Yeah, yeah, I've seen it.
it's pretty cool. This is the depth map. All right. So yeah, I think finding correspondence is important. Like you take different orientation of images in your scanner or camera, but how the the key points in those images are correlated, so that is important. Semi manual, fully automatic. Yeah, key points translation. So hmm. Yeah, so this is gonna be a challenge where let's say you take images from different orientation or angle or height. There is a
Mhm.
problem of scale, illumination, rotation. So
Yeah,
how the key points in first image matches to key point in second, and you build upon it. So they're saying key points in discriminative descriptive features that is invariant to scale. So features like edge corners, shift and surf using local neighborhood gradients in images. So I think uh, they're developing these local relationships, and even like in checking in various orientations in the next image, and if these local relationships are there, uh, the key point can be automated.
Yeah, and then they talk about stitching and problem you told about, that whenever you yourself do the scanning, it's difficult to get the first starting and end point together. So for the image based, it can be done via stitching, but for 3D, it's difficult, right?
Yeah, like there was like this alignment issues. So let's say this is a plain image where you start scanning from this orientation, you go in a loop and get back. I have seen like once w- it will generate like a real time 3D in your interface of this all objects based on the depth map, and you start doing this and you come back many times. Your last frame doesn't align with the first frame you started, and that's called like an alignment issues. But yeah, so, okay, let's see. So they're saying it can be fully automatic using key points, match features between images to find correspondings. Once the correspondence are identified, remove the outliers, capture the necessary camera data, and then project any pixel in 3D. This is correspondings. This is image stitching. So the way I'm forcing is once you identify those key points, and once you stitch all those images, you you can identify the camera position and then do overlapping of those images, that okay, from this position the image is like this and another camera position is like this, and then you can stitch based on after aligning key points.
Yeah.
Cool. Panorama. Building Rome in a day using image to 3D point clouds. So that's kind of so this is on construction sites. This is like professor from my college. He has a really cool startup called Reconstruct.
Yeah, it uses computer vision to check on scheduling, whether
Yep.
it's on time, delayed, or before
Correct.
time.
Mhm. And like depending on your devices, like drone, using robot, phone, it affects the accuracy level because like what's the pixel per inch, and then they're doing 3D construction. So in this example, they're checking what's the as built versus the ideal position of that element and compare, also augmenting that reality with that data. So I think getting tolerances, and as you can see, these points reflect the point scan in that site. So you can play with the visibility. So one we had a discussion yesterday uh, for our department where there was a symposium on architecture technologies and he gave a presentation. So think there was one question that what would be fully automated 5 years from now, and his reply was like construction monitoring would become more and more automated, and also like AI is currently at that uh, development that this can be done, and they are integrating it with scheduling as Rutvik pointed out. So I can scroll through the timeline, see the development of those elements. So very good application of CV in construction. Cool. So they're saying 2D are not as accurate. 2.5 becoming commodity, cheaper, lighter, static versus handheld, and spot uh, from Boston Dynamics. Experts versus anyone can scan applications. So basic training, what's the cost, deployability, and accuracy? These are the factors you might consider when you're doing those operations. Cool. Oh, it's 1.5 hours already. Anything else you wanna talk about in this lecture?
No, I think we can move on to the fourth one.
Awesome. Yeah. I was reading more like uh, they are sharing like more kind of a sensor 3D reconstruction. Maybe like sometime in future. I was interested in like what are some machine learning models who are doing 3D reconstruction.
Mhm.
Mm, that is interesting thing to discuss. All right, lecture 4, segmentation and clustering. We saw this high level semantic versus low level. Yeah, so the low level identifies like I might need to check, but from my understanding, I think they are dividing the pixels into grid, and then based on the similarity, I think this is super pixel, which identify identify clusters of regions which shares similar pixel value. Or
So it's like a 5D approach where you're taking X, Y, Z as well as color and position. I think that's what super pixels is.
correct. Hmm. Yeah, I think there is a slide where they're talking about 5D. So definitely there is something we should discuss. Uh, Again, how much do you segment? Like problem of over segmentation, under segmentation, same algorithm, different parameters. So a lot of times I've seen like many of like edge detection or clustering algorithms. You might need to do like trial and error of different parameters, and then you find an ideal range which works for you for your problem.
Yeah.
So this is watershed, requires a grayscale catchment basement. So it's yeah, from watershed you can see start flooding the landscape, local minima. Hmm. This is another algorithm. It's using graph-based merging segmentation. Hmm. Yeah, I think they're going like what are some characteristics of this algorithm. Numbers highly depends on local image contrast. Cool. Mean shift, color and position of each pixel, find clusters in this distribution.
So here's where the machine learning part starts, and it's like a clustering according to pixel information.
Correct. Yeah. I'm not sure which machine learning algorithm they are using. Because like clustering sometimes also like falls into statistics without machine learning. Hmm.
They have connected it, I think,
Oh,
for the slide.
okay. Then yeah, cool. So we saw different, like 4 or 5 clustering approaches, and this is superpixel, closely related to mean shift, and as Rutvik was pointing out earlier, it uses 5D space, color plus location, traits of color similarity and proximity.
And these are the two parameters, like you were showing the image of, I think you worked on Zahadi's image where you were doing the hook transform, and because you, I think, increased the radius, they were too less, or I think you reduced the radius because then there were too many circles detected on that image, right?
Yeah, it was too many size. Like I should have reduced the number of circles.
So I think that's what this is. The number of segments is the clusters uh, around which pixels will have same information.
Correct. And like depending on the number of segments, if there are a lot of segments, it there's a problem of over segmentation. If there are very less segments, there's a problem of under. So
Right.
choose this parameter wisely. Cool. And I think this gives a comparison of all the clustering algorithms we saw earlier, and this gives various output. So it's a different way they treat clustering because yeah, and depending on their approach, it gives different output.
And Felsen's Wolves is performing well on detecting or segmenting different features present in that site location.
Mm-hmm. Correct. Yeah, I think like different algorithms have some background. So we saw watershed algorithms. So maybe sometimes when you're doing landscape or analysis for CV, you might use that. For construction, you might use this. Even looks like this kind of give me a feeling of like states or country division maps, and maybe compact watershed can help in forming those clusters very well. So
Yeah.
cool. So the key takeaway would be to be aware of what are different clustering algorithms and what are the parameters you can change, and depending on your end goal, you play with the parameters and identify which algorithm is giving you the best results. So I think there's no like hard defined formula, use this for your problem. So
Yeah.
it's
Yeah.
cool. So I think they're showing more images here. Then point cloud segmentation. Yeah. Clustering usually ignores the pixel layout, and neighborhood segmentation relies on spatial cues and constraint. And they are sharing like various algorithms and their clustering approach. So the way they treat outliers, the way they form the clusters are a bit different in each of these. Popular key means clustering for a lot of machine learning approaches. Yeah. So do you wanna talk anything about this slide?
No, so I was saying like they were mentioning the clustering related to machine learning. So the clustering key means I think they're using for superpixel and even super voxel. They've not talked about super voxel, right?
Uh, it it says here used in supervoxel, but yeah, I'm not sure. Yeah. So I think like this diagram pretty much gives away how the algorithm works, where you just randomly select points, do the partition, and then recalculate uh, the mean and form another partition based on the mean, and that's how you will iterate and form this
Yeah.
clusters.
So you can even manually define k, like number of clusters you want, or you can even keep it to machine to choose the optimum k value. You do that using the elbow curve method.
Correct. So many cases, if we don't know and don't want to do try out different key values, you can automate and ask the machine try different key values, give me the best, which has the least uh, error
Yeah.
rate. Cool. Finally, we are into machine learning. No, cool. Uh, as you saw, this is handcrafted like algorithmic approach can be done through CV, one of the and canny edge, Visa, corners, shift, feature learning using k-means. So this part is being replaced with machine learning, and even handcrafted features can be replaced to learn features from deep learning. Okay, so there are two major components, features and algorithm. You can replace both feature identification and algorithm through machine learning or deep learning pipeline. Cool. I think this goes into like basics of machine learning, what's supervised and unsupervised, and
Yeah.
that is one thing which you can easily find online and covered in. Uh, I think I talked briefly in one of my past live stream. Oh shit! Cool. Do you have anything which is important for us?
I think I had the Airbnb example where they they're using all the algorithms. Say they're also using regression, classification, and even clustering. For regression, they're using to predict the pricing of the listings provided. Segmentation, they're using to check on the number of features they have provided. Say they have provided this furniture in their the user has provided it, and to validate it, they're using segmentation, and again clustering for scene detection, like indoor or outdoor.
Correct.
And that one article had all the algorithms of all the types of machine learning, you can say.
Right. I see. So I think based on that, like few things which to keep in mind is like for supervised learning, classification and regression, and this is a really good image where they are classifying different objects and using regression they're predicting the boundary box.
Yeah.
Correct. Same. various objects, classification, the bounding box, regression.
So it's again, you need to prioritize what output you want.
Hmm.
Just a basic approach.
Yeah, basic like image classification workflow. You train, test, validation data, feature identification using like a deep learning model. It can be convolution or whatever model you want, and then classification output. You do training. This is a learn model with features and classify. And you might have like seen a typical convolution neural network where in the initial model layers, it's identifying low level features like lines, uh, let's say for human example, like eyes or like various small level features. And then as you go deeper into the network, yeah, so initial layers are low. As you go deeper, it's very high where it's able to identify shape, face.
Specific features, yeah.
Mm-hmm. Correct. Cool. So yeah, artificial neural network, it's called deep because the number of hidden layers are deep and like cool. So think they talked about different activation functions. All right.
And the class project. Yeah.
I think a good next step would be playing with the algorithms on OpenCV, trying out with different hyperparameters so one can understand what's going on. And yeah, let's maybe conclude. So what we uh, learned from this lecture is how one can detect edges and what are the challenges in edge detection, what are various algorithms in edge detection, how you can simplify lines, circles, shapes using hug, transform, or Renset, and then clustering algorithms. What are the various clustering algorithms available out there? Their hyperparameters and how we can play with them to do clustering for your own images.
Yeah. And one thing I liked is the on-site examples and references they have provided.
Yeah, and so Rutvik, what do you think? Like, what some other examples currently in the industry which are using computer CV?
Okay, so I can tell about one example which we are using at DBF. So what we are doing is we wanted to preserve the on-site trees because it can add value to the users and customers using the tools. So what we are doing is using the satellite imagery. We are detecting the trees and then modeling them into the tool. So that's one approach, and then another one is to analyze the urban heat context or to rate the neighborhoods depending on greenery, water bodies, and this all can be done using just the satellite imagery data. And since it's available widely, so to think on a global level, it's easier. But if you go on detail, you can get some more data and you can model some more algorithms in it.
I see. Interesting. And like few of the ways I see CV can be deployed is one on construction assembly, where you can use those vision models to arrange those elements. It can be in facade, MEP layout, partitions. Another is scheduling, as we saw with reconstruct, where you can monitor and do real-time update in your scheduler. Third thing is, I, I think with remodeling, you can use that point cloud data, try out various design options, and also with this highly detailed site monitoring techniques, there could be uh, more information transfer from construction to designers, because there are uh, frequent visits, not so frequent visits by designers on site. So maybe using this approach, those information gap can be minimized.
Yeah, I think I also came across one idea where last week one of our participants at the workshop, he had an interesting idea where he was trying to relate the Google Street Map images to the price of the houses. So what he wanted to do is, whenever you provide a street view of any house or building, he wanted to predict the price of it. So we have the, he was I think based in Australia, Melbourne I think, and we had the Melbourne housing data and we even had the Google Street View images. But how to correlate them, that was an issue.
Ah, I see. Cool. It's almost on like 2 hour mark, so I don't want to stretch too long. So let
Yeah.
me make an announcement for the next session, and we can also talk about DBF and the opportunities available. So the next session we have is with Sergey Pigash, and we are doing some hands-on Rhino plugin development, and he's it's using like with MVVM and material design. So even I heard MVVM for the first time when I was interacting with him. So I'm quite excited to learn about him, and also like his journey from computational designer to software developer, life at Code Studio. So there's something on schedule on next Saturday.
Okay, so even I have an announcement like at DBF, we are going to be focusing on an interesting project this summer. So anyone who is excited about using machine learning in built environment can feel free to connect with me, contact me, or even contact the other people at DBF by sending your applications or your interest.
Awesome. And yeah, I have seen the growth of DBF, and it's the team is growing very fast. They are implementing a lot of new features, and it's a really good place to be at in if you're really into technology, pushing cutting edge things in AEC. So thanks a lot for sharing that opportunity.
I think you're doing a great job by building this community of people who are interested in tech AEC.
Thank you. And thank you, Rutvik, for doing this collaboration. Hopefully when the all the lectures are uploaded, we can do another live stream of from lecture 5 to the rest of the lectures, and
Yeah,
I
absolutely.
enjoyed it.
It's interesting. Thanks a lot for inviting.
Yeah. All right, have a good rest of your